This is our last set of notes for this unit. We're almost at the end. The double angle identities is kind of similar to the sum and difference one, but instead we are multiplying by 2 instead of adding or subtracting. Like the other ones, this is something you don't need to memorize, these formulas here, but they'll be given to you on a formula sheet. You just need to know how to use them. So let's take a look at some examples of how to use these. This first one tells us to write it as a single expression. Well, I had to compare what's given to me here with the ones up above. And if I take a look, well, this looks pretty similar to this one, but I probably need to factor this out first and see what I get. So I can probably factor out a 3 here. Once I do that, I would get 2 cos squared theta minus 1. Okay, now that looks like this identity over here. So I'll replace the stuff in the bracket with cos of 2, and my angle is theta. And you know what? That's all I can do. And I can't evaluate it because I don't have an angle, so we leave it as is. That's it. The next one, let's take a look to see what that one looks like. Well, I have a sine times a cos. That leaves me with this one. This one is the only one that has sine times cos. I'm left without a half. So that means that I probably need to times this by a half to get rid of the 2. And then I have sine of 2 pi over 3. Because, remember, my angle goes in here, and it has to multiply by 2, by this formula. For example, sine of 2 times, and my angle is pi over 3. So I just simplified it and put it together, so I'll have 2 pi over 3. And the half I put at the front is because we're supposed to have a 2 when we expand, but here's missing the 2. So then I have to show for that. And if I want to expand this right now just to check it looks like this, I can. I can always check my work by going the other direction. Okay, so if I want to expand this, this would be 1/2. And then I'm going to change this portion into its formula, which is 2 sine times pi over 3 cos pi over 3 And if you look at that and compare it with the question that we have down here, it's the same thing once my 2 cancels out. So I know that I put this under a single trigonometric ratio perfectly. So I'm just going to erase all that. You don't need it. Okay. So I know how to evaluate sine of 2 pi over 3. Remember, we're going to use our reference angle of pi over 3 to do this. So I can draw my triangle. Okay, sine of pi over 3 is root 3 over 2. And the 2 pi over 3 means it's in quadrant 2. And sine is positive there, so I just leave it as is. So then my answer should be root 3 over 4. And that's it. I put into a single trigonometric ratio at first over here in the beginning, and then I evaluated by the end. I got my exact value, and that's it. Moving on to example 2. Now we're going to do some more proofs, but using the double angle identity here. Okay, we're going to take my left-hand side because that's the most complex looking. These ones are pretty obvious of where we need to start. Like we want to get rid of that cos 2 theta and sine 2 theta. So 1 minus cos 2 theta, well, if we looked at our identities up here, I have 3 to choose from. But I have to be smart about it. So let's take a look again at what we have. Well, with sine 2 theta, that automatically becomes 2 sine theta cos theta. I only have one identity for sine 2 theta, and I have to use that one. Okay, cool. And now to take a look at the others, I can either change it to 2 cos squared minus 1 or 1 minus 2 sine squared theta. So the other one, this one up here, probably we won't use for this one because if you just take a look, it won't really do anything for us, really. So it's probably going to be one of these two. How we're going to determine that? Well, let's take a look. I want this to become tan. So far, if I think about what tan usually is, it's usually sine over cos. And maybe I can somehow manipulate this so that I have sine over cos. That means I need to get rid of this sine theta at the bottom here somehow. So maybe I should change it with this formula right here. So the sines can maybe cancel out somehow. So let's take a look. Let's plug that in and see what we get. Okay, but then we have 1 minus 1, so that's gone. I'm just left with a positive 2 because of the two negatives there. Will cancel to become a positive. So now I'm left with this over 2 sine theta cos theta. And look, the 2 cancels out. One of the signs cancel out, so I'm just left with sine theta over cos theta. And it's perfect. That's tan theta. And now that's my right-hand side, and we're done. It always feels really satisfying when you are able to solve for this, to show that left-hand side is equal to the right-hand side. Here's the next one. Our most complex side looks like it'll be the right-hand side, so let's try that and see where it goes. Sine squared theta plus cos theta. I'm just expanding already. This would be 2 sine theta cos theta plus cos squared theta. So all I did was expand this already because that's sine theta plus cos theta times sine theta cos theta. Sine theta plus cos theta. That's what I did. I just did my rainbows there to get this numerator. And then my denominator, I can change that already, sine 2 theta. There's only one identity for that one, which is 2 sine theta cos theta. Okay. Well, take a look at this. Sine theta, sine squared theta, and cos squared theta. Doesn't that sound like a familiar identity to you? It should, because sine squared theta plus cos squared theta is 1. That was from a previous identity from before. So then we can replace that with a 1 instead. And we have plus 2 sine theta cos theta. Let's separate our fraction, or the numerator of fraction. So we have 1 over 2 sine theta cos theta plus 2 sine theta cos theta. Oops, there's supposed to be a theta in between there. I'll fix that a bit. Okay, well that cancels out as a 1. And then, if I take a look at what I actually want, I want cosecant 2 theta. Well, I can actually rewrite this back to 1 over sine 2 theta. Because remember, sine 2 theta is 2 sine theta cos theta, and then I have plus 1. Okay, Well, I can change it to cosecant theta, 2 theta, by doing the reciprocal of it. And that is my left-hand side. And then we're done. Perfect. The very last example of this unit. Okay, now this is a looks like a double angle identity right now. But then I have a cos and I have a sine. And as I've said before, we kind of like to deal, if we can, have consistent trigonometric functions to solve for. Well, because now I know my double angle identities, I can replace this cos 2x with the identity that has sine in it. So it's 1 minus sine squared theta, or x. And then on the other side, we still have 1 minus 2x, 2 sine x. Well, this is something I know how to solve from before. I'm going to move everything to one side, equal to 0, and then I will factor it. So this is the same thing as 0 is equal to, I think there's supposed to be a 2 at the front here that I missed, but it'll be 2 sine squared x minus 2 sine x, and then I can factor it out at 2 sine x. If I do that, I'm left with sine x minus 1. So remember, we're going to solve for this on one end and the other end. So I'm going to split it down the middle like this. So I have 2 sine x equal to 0 to solve for, and then I have sine x minus 1 equal to 0 to solve for. So once I simplify this, I get sine x is equal to 0, and this one would be sine x is equal to 1. If you look at our domain, we want it to be from 0 to 2 pi. We can draw it out on our unit circle to help us figure out what my values will be, or what my angles will be. So sine theta, or sine is 0 whenever we're on the x-axis. And that occurs at 0 and occurs at pi. One is sine 1, it is only 1 when we're over here at 0, negative, or 0, 1. And that's at pi over 2. So that means x is equal to 0, pi over 2, and pi. And then we're done. That's it. So this is our entire unit. You have your tests that will be coming up very soon, so we'll be practicing more in class.